When we did right triangle trig, that was all of your SOHCAHTOA stuff, correct? And we talked about that last Thursday where you worked with SOHCAHTOA. And the sine of an angle is what over what?
Opposite over hypotenuse.
Opposite over your hypotenuse. Cosine.
Adjacent.
Just figure that out.
Opposite over adjacent.
And then your tangent is opposite over adjacent. Now, in a right triangle, there is one side of that triangle never, ever, ever changes. It's the hypotenuse. The hypotenuse will always be the hypotenuse, and it will always be across from the right angle. We do not concern ourselves with the trigonometry of the right angle until later when we start worrying about the quadrantals. Yes, sir?
What's the symbol?
Angle. It's an angle symbol. Actually,
I got
it's.
you. You just
I put an arc in it. That way it makes it look like instead of an L or a less than symbol. What I should have done is this, is use theta, because your book uses theta for this.
Yeah, now we're talking.
So we have sine of theta. We'll just put that in there now. Theta is just what they use as their angle symbol. Okay. Remember when you're dealing with trig, and this is what you guys were working on Thursday, it wasn't that big of a deal. If you pick an angle, one of the non-right angles in the triangle is just a matter of perspective as to what one's going to be your opposite versus what one's going to be your adjacent. And it's not that big of a deal. So in this case, this would be my opposite, and this would be my adjacent. Okay? This wasn't difficult. You guys went through all this rather easily when you were solving those right triangles. But what I want to do is introduce you to the inverse trig functions. No, you use the inverse button to solve for the angle, the inverse sine, that sine to the -1 power. But there's actually 3 trig functions that are called the inverse of these. So you've got your 3 inverse functions of sine. Well, here's your sine, cosine, and tangent. This is your cosecant, secant, and cotangent. Those are the 3 inverses of sine, cosine, and tangent, respectively. So cosecant is the inverse of sine. What's that? No, it's just CSC, I guess. Hey, didn't you guys just ask about the park schedule? Look, I got an email about it. So we'll figure that out later. What happens here is to get this cosecant, oops, do that yet. If you do this, 1 over sine. 1 over sine would be the inverse of sine. It's the reciprocal. Okay? If you do that, you know that that means it's 1 divided by the sine. Sine is what over what?
Opposite over hypotenuse.
So what happens here is you do this. It's 1 divided by the opposite over hypotenuse. And then you multiply by its. So the inverse of sine is hypotenuse over opposite. All you're doing is you're just flipping the fraction. Okay? Same thing with secant becomes hypotenuse over adjacent. And then what do you think cotangent's going to be? It's tough.
But is this the inverse?
Yeah.
Oh, you're just using funny names for that? So the inverse of sine is cosecant.
Yep.
Versus cosine is secant.
Yep.
And tangent is cotangent.
Correct. Those are your inverse functions. Okay. They're just the reciprocal of them. Now, what we do with this is we just, for now, we're just using them as trig functions. We're going to list out what they are of a specific theta in a triangle and work our way through all 6 of them. For example, yes, ma'am.
Wouldn't the last one be adjacent over opposite?
Oh, thank you. I said opposite. I just wrote hypotenuse.
So these are inverse.
These are your inverse ones. These are your newest ones. People always want to say cosecant goes with cosine because they both start with C's, but they don't, okay?
That's cotangent.
Yeah, it's one of those things. So just remember, if you put them in order, cosecant, secant, cotangent, just remember that's the same order as your sine, cosine, and tangent. Like I said, we don't use a lot of it quite yet, But eventually, when we start doing a little bit more of the chapter 14 stuff, the inverse trig functions come out a lot. Right now, it's just kind of identifying. So, quick example. Let's say you have a right triangle. And we'll make it easy. We'll say it's a 3 and a 5. And I want to do my 6 trig functions of theta.
So you want to do sine, cosine, tangent, and then cosecant?
Yeah.
And if you do all 6, will you be able to solve it?
Yeah, you can. You can do that, but right now I just want to list out all the 6 ratios. And that's all we're doing here. So if I'm missing a side length, you'd have to use good old-fashioned. Well,
We know it.
all right. Use Pythagorean theorem where you recognize triple. Triples still come back every once in a while. You see the 3, 4, 5s and 5, 12, 13s. So your sine of theta is your opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is your opposite over adjacent. When you go through your inverse ones, all you have to do is flip the fractions all the way through. Okay? I should have given you a root. So the inverse here would be what? 5 over 3. And then
What exactly does this tell us?
I'll show you. All it is right now is just showing you what the ratios of your sides are. It's that you're not trying to find the angle, you're not trying to do any of that. We know how to do that because you hit that second sine button of 3/5 or whatever it might be. But for this, in this case, we're just worrying about how do you write it out. Okay. We're not worrying so much about the angle yet. But what this will allow you to be able to do is this. Let's say you're given the secant of theta was, I don't want to see. I'm going to do this. What are all of your other trig functions?
So we just have to go through and make our triangle and
Right. So if you know that the secant of theta is 13 over 6, cosine is 6 over 13. Now, think about what you have. If you have a secant value of 13 over 6, what's the 13 have to represent? It's the hypotenuse. Now, when you're into these triangles like this, it doesn't matter which angle you pick as theta. It really doesn't, because it's about perspective. Okay. So if secant is 13 over 6, where's the 6 going to go? Is it your adjacent or is it your opposite?
adjacent.
Your adjacent. So adjacent here would be,
Yeah.
and then how do you figure out your opposite? Pythagorean theorem. So what's that? 169.
So 36 minus 36.
It's about 11 and a half.
It's just going to be
And then you take the square root of that.
square root.
Do you guys remember how to simplify square roots with your calculator? Because you have to have simplified radical form. There are no decimals.
Oh yeah, you get those small calculators.
What was it? Right, but your calculator does it though. Go to your table. Y equals, and what do we come up with here? 133? Take 133 divided by x squared. I think we've talked about this before.
Probably.
If you go through your table, you're looking for the smallest value in the y column that is still integer. The x column is what goes out from the radical. Now, in this case, there isn't anything, because after you get back with 1 and root and 133, everything else after that is just all decimals, right? And it just goes on. So that means this can't be simplified. On the other hand, try something different. Let's say it's y equals, put in 108. You should be able to just overwrite that. You put in 108 and now go to your table. See how I have 6 and 3?
So you have 6 and 3.
So that would be your answer, 6 or 3.
Because it would,
Does that make sense? As you continue through your columns, you're looking for the last value that's integer, and y, before it becomes
36.
correct. So these calculators will do this for you. It's just a matter of knowing how to manipulate it. Does that make sense? Works the same way if you have to do a cube root too. Works the exact same way.
So just write root 33.
Yeah. So in this case, that means your opposite would be root 133.
Oh man, now we're gonna have radicals.
Yeah. So this is the weird part where you just have to be careful about rationalizing. Now, what's nice is you already know what your secant is. So if you know what your secant is, that means your cosine would be 6 over 13. We okay on that?
Yeah.
We know that our sine value is 133, root 133 over 13. The cosecant would be its reciprocal. So that would be 13 over root 133. No, because you have to rationalize it. Remember, you have to multiply the top and bottom by that radical. This isn't so bad because what's the square root of 133 times the square root of 133? 133. So your cosecant becomes 13 root 133 over 133. Okay? It's just a matter of going through it like that. And I'll let you guys figure out tangent cotangent. It's not that far. Does that make sense?
Yeah.
That's what we're using these for now, because you can be given any one of the 6 trig functions, and you can figure out everything else. Right? Does that make sense?
Is there like a saying like so the taller the universe?
Not that I know of. Never heard of one.
You should come up with
Yeah, exactly. Don't give up your day job. Also, that goes back into remembering these. Your special right triangles. Everything after we get out of the these 13.1 and 13.5, 13.6, everything else we do for the next 3 weeks worth of trigonometry stuff, or even a month worth, is all going to be based upon the special right triangles. 45, 45, 90, 30, 60, 90. Now, do you recall your side values in a 45, 45, 90?
X.
X. X.
2x. X root 2.
X root 2, okay. What about 30, 60?
That's, so that's x over there, that's x root 3.
Where?
Down after 60. And then 2x.
Those don't go away. As well as all the special right triangles themselves, the trig functions of them, you're going to know them by heart
Yeah.
real fast.
Real.
Okay? Because like I said, everything that we're going to do is built off of these triangles as we get to it. All right? So the quicker you're able to figure out and work with your trig functions on your specials, the better you're going to be. For example, excuse me, if I want to look at my 45, oops. Can I write it as 1, 1 and root 2? X, X, X root 2, just put them all as ones? Is that all right?
Yeah.
If I want to do the sine, what's the sine of 45?
Sine is opposite over. So it's going to be 1 over, yeah.
So it's
Root 2 over 2. Oh.
Okay. What's the cosine? Same thing, isn't it?
Yeah. Because adjacent and opposite are the same.
Therefore, your tangent is
Opposite over adjacent, 1. Yeah.
1. Right. Tangent in this case is 1. Now, when you do your reciprocals, would it be easier to reciprocal the root 2 over 2 or the 1 over root 2?
Yeah.
Notice it's quicker and easier to do the reciprocal here. Because that's what it was opposite over hypotenuse. So hypotenuse over opposite is just root 2. That makes sense? You're just flipping it.
If you did it the other way,
If you did the other way, you have to rationalize it and you wind up simplifying it.
and then it would be 2 2 times root 2 over 2, yeah.
And it winds up simplifying. So your secant value is also the same, and your cotangent is also 1. Okay. Not so bad. These are very easy to work with. You guys, even if it's something that you don't remember, it's easy to fill this out and write it out real fast, just by looking at your triangle.
I was just going to take some algebra.
How?
Yeah, like what are you
Because eventually you're going to do this.
I mean, I understand that you're very.
And you're going to do this over how do you put this? We're going to do this into intervals. We're going to look at different quadrants. And then when we do this in different quadrants, we have to know in terms of gradients to pop around between the different quadrants. Because every one of those values, that's 45 degrees, right? If I say it? That's 45 degrees coming up this way. That's 45 degrees coming that way. And I can do this also having being 45. And each one of those values has a different, has the same sign, just different sign, S-I-G-N, one in the quadrants. This is the algebra that comes out of it. It's just a matter of knowing this quickly. Same idea, like I said, if you're doing the 30-60. If you're going to build that out, I would say it's 1, root 3, and 2, and just list out all my things. Same thing with the 60s. You want to take, we got time really to list them out. So the sine of 30 would be 1/2. Cosine would be your root 3 over 2. Tangent is the 1 over root 3, which is root 3 over 3. Okay. Flip them all for all of your inverses. So the cosecant of 30 would be 2. The secant of 30 would be 2 over root 3, so it becomes,
2 root 3 over 3.
very good, it's 2 root 3 over 3. And then lastly,
Take the root 3.
it'd just be root 3. Okay. Now, as we get going into these, you'll start to find real nice, easy patterns. Same idea with the sine of 60. You'll notice that the sine of 60 is the cosine of 30. The same thing. Root 3 over 2. The cosine of 60 is the sine of 30, 1/2. And then your tangent. It's just root 3. Tangent opposite over adjacent. You're going the other way of the other stuff. Okay. Like I said, there's not a lot of trickiness involved with this because these are your basic trig functions you guys have all worked with in the past. It's just a matter of writing them out. Okay. I'm not going to write out the inverses. I'm sure you could figure that out. Remember to simplify. Okay. Oh, where was the next bit here? That. Also, it allows you to do quick solving for missing side lengths.
5 root
In this case, it is what? 5 root 3. It's 5 root 3 in this case because it's a 30, 60, 90. And you knew across from the 90 was 10. Remember that, set up the algebra that way, work your way out of it?
So that's 5.
Yep. You always have your factor to it. It's not a difficult thing. I know you guys got beat over the head with this last year a lot. So this should be just a lot of refresher today. Same thing, we did this on Thursday. Remember when you're solving out the right triangles? I talked about this a little bit on Thursday about reusing givens. I want to explain again why I say that. If we're going to solve the right triangle, obviously you're giving you an angle and a side. You fill in what you know. Here's your angle. Here's your side. Okay. From there, we agree that we have to find the hypotenuse, and I have to find the adjacent in relationship to that angle. You guys agree? Now, let's find the hypotenuse first. What trig function am I going to use to find the hypotenuse?
So far.
Sine. In this case here, when your variable's in the denominator, what do you do to solve for it? Remember the shortcut? Switch them. Works every time. Here's what I want you guys to get in the habit of doing. Write down what you're going to do before you put it in your calculator. Okay? Seriously, write down what you're about to type in prior to doing it, because it's so easy to type in, accidentally type sine, or if you put this in, you go 12 divided by a sine of 22 by mistake. But you wrote sine of 20. You're going to be wrong if you don't show me. You know what I mean? Show me what you're doing. And this is the other reason why I say to reuse your givens. Let's say you accidentally did type in sine of 22. You got your hypotenuse to be some number, and it's wrong. If you reuse that wrong value here to find this side length, are you going to be right? No, you're never going to be right. But if you did write down the wrong value for your hypotenuse, what's the different trig function you could use to find this side that didn't use it? Tangent. Does that make sense why I say to do that?
Yeah.
You want to reuse your givens as much as you can to alleviate the possibility of screwing up. It's not a difficult thing to do. It just helps you to make less mistakes. Okay? It's not to say that you would make a mistake, but it's taking that variable out. All right? And then obviously the really easy part in this case to find the missing angle is to subtract.
Yeah.
Because remember, the two angles within a right triangle that are not right are always going to be complementary. So that has to be set. Okay? So please try to reuse your givens as much as you can. I then know to write that on tests and quizzes to remind you. That way you don't screw up. Okay? Yes, ma'am.
So, on things we ask us to solve the right triangle, do you just want us to find the angles and sides?
Yep.
Okay.
Yeah, whenever it says solve it, you're going to find everything you can.
Okay. But I mean, you don't want us to find the cosecant.
It'll say write out the 6 trig functions.
Okay.
It's pretty blatant when it does stuff like that. You know, we'll have stuff like that. All right. So there's that. We don't need to do another one. Do you vaguely remember elevation and depression?
Yes.
Vaguely.
You guys did that in lab last year, I think, in the auditorium.
Yeah,
You worked with angle and elevation a lot. We were measuring how many degrees we were off center
Yeah.
to go up and down. Well, with the fact that we're missing 50% of our class, I'm just going to stop them now before it gets too much. And we'll go into depression and elevation stuff tomorrow. Bye. Very well. Okay? Let me get some problems. What numbers were they? They were 19. Not 34. 38. Real fast, when you are working with the area of a regular polygon, do you remember the formula for the area of a regular polygon?
It's something minus the outer.
No,
Yeah, it was. Not
Something
minus.
about the radii.
the area
Yeah.
of a regular polygon.
Yeah, it was something with the radii and all the angles and all
It had stuff to do with angles, yes. But it had, do you remember this? 1/2 perimeter apothome?
Yes.
The apothome, yes, the apothome, the apothome. Yeah. Did he say apothome?
I don't even know.
No,
He said it.
half like the perimeter.
It is an opossum, yeah. It's just like an opossum.
Wait, so is that the straight line or the angle?
Well, the angles, if you think about the angle parts, if you're talking about a regular polygon is when it's inside a circle.
It's from that to
If
the
it's,
side.
if it's to the sides of
That's what
the,
radii says.
that's the radius, so it's the other one.
It's what forms the 90-degree angle, yeah.
Correct. All right? I'm not giving you any more instruction on that, let you figure out the rest, but yeah, you're right, you gotta remember how to work with your angles on that.
Thank you so much.
Yes, sir. All right, go ahead and get started, I'll pull it up on the board here in a second.
Thank you. Do you